In this video, we're going to talk about measures of variation. The first measure of variation, and this is the easiest, is the range. So the range is the simplest to calculate. Literally, all we do is we take the max data entry and we subtract it by the minimum data entry. Okay? The downfall, so that's the advantage, is it's simple. The downfall is that it only uses 2 data points. Okay, the max and the min. Alright, so that's the downfall. It doesn't take into account any of the other data's points. Now, we need to come up with another way to measure variation, and that comes with the definition of deviation. So what is a deviation? A deviation of some entry data point X in a population data set is the difference between the entry X and the mean mu. So a deviation of X is defined to be X minus the mean. So it's basically saying how far away from the mean you are. Okay, so how far away from the mean you are. All right. So if that number is positive, then you're on the right side of the mean. If that number is negative, you're on the left side of the mean. Okay? So it kind of tells you where you are with respect to the mean. So we have a definition. The population variance. The population variance of a population data set of capital N entries is defined to be sigma squared. So sigma squared right? And this is defined to equal the sum of the data value minus the mean, so the deviation of X, and then I square it, and then I add all those up, and then divide it by capital N. Okay? So that is the formula for population variance. Population variance formula right there. Sigma squared. Okay? The population standard deviation is developed because when you look at population variance, you're talking about squared units. And if you have squared units, say your units are dollars. So you're talking about money, right? What does square dollars mean, right? It has no meaning. It's meaningless. Okay, so we need to come up with a way to not have square dollars. So how do we get rid of square units? Well, we take the square root. So this measures the variation of the data set about the mean, and it has the same units as the data set. Okay? So this is sigma equal to the square root. All right, let me do this. So square root of sigma squared, which is the square root of the sum of X minus mu squared over capital N. Okay? Now, why do we need, let's see here. why do we need sigma to describe a population? Okay, that might be the question, all right? And so before we get into this question though, I want to talk a little bit more about sigma. Sigma is a value that cannot be less than 0, so it's 0 or greater, okay? The smallest it can be is 0, and if it's 0, so if you have a sigma equal to 0, then all entries have the same value. Okay? All entries have the same value, right? So as sigma gets bigger and bigger, the entries get further and further away from mu. So as sigma gets bigger and bigger, the entries get further spread out from the mean. Okay? So your value for your population variance and standard deviation will always be non-negative. Okay? It'll be greater than or equal to 0. All right? That's what we're saying there. So why do we need sigma to describe a population? That's a good question. We're going to illustrate this with an example. So I give you two populations. Population 1, this frequency histogram, we're going to have 1 in the 1 category, 1 in the 2 category, 6 in the 3 category, 1 in the 1, and 1 in the 5. Okay? In the second population here, population 2, we're going to have 3.5 here. We're going to have 1 here, 1 here, 1 here, and then 3.5 here. Okay? So what are we going to do here? Well, first thing I want to do, I'm going to calculate the mean of the first population. So say all we knew how to describe a population with was the mean. So the mean of this first population here, well, how do I find the mean? It's the weighted average, right? So it's the sum of the x times the weight over the sum of the weights. So what is this equal to? Well, this is, the first one is 1 times 1, okay? The second one is 2 times 1. The third one is 3 times 6, okay? And then the fourth one is 4 times 1 and then 5 times 1. Okay, I'm going to take that and divide by the weights. So what are my weights? My weights are 1, 1, 6, 1, and 1. So 1 plus 1 plus 6 plus 1 plus 1. So what does this add to? So in the numerator I get 30, in the denominator I get 10. So this gets me 3. So mu1 is equal to 3. Okay, so that population 1 has an average, a population mean of 3. Now population 2, okay, when I do mu2 for population 2, so I have 1 times 3.5, 1 times 3.5, plus 2 times 1, plus 3 times 1, plus 4 times 1, plus 5 times 3.5. Okay? I take that and I divide by what? 3.5 plus 1 plus 1 plus 1 plus 3.5. And so when I add this up, what do I get? Well, I'm going to get 30 over 10, which is 3. So what does that tell me? Mu2 is equal to 3. So if the only thing I knew was, or how to describe a population and was by the mean, then I would have a mean of 3 here, and I would have a mean of 3 here. And so mathematically, if that's all I had to describe a population, I'd have to say that those two populations are the same. Clearly, we can look at this and see that this population is very different than this population here, okay? So that, is, my friends, is why we need sigma to describe a population, so that we can tell the difference between population 1 and population 2. So let's calculate the standard deviation. Okay, so let's try it, see if we can do this. All right, so sigma squared. Okay, so for this particular one, right, so we've got x values. So we're going to use these midpoints as our x values, just like we would in a frequency histogram. All right, so what is it? The first one, so if you think about the formula, it was x minus mu squared, right? So the x value, the first value is 1. So I do 1 minus mu. What was mu? Mu was 3. It was the average. 1 minus 3 squared. Okay, and there's only one of those. Okay, so there's only one of those. Then I have 2 is my next data point. So my next x value is 2 minus the mean, mu 3, okay, squared. And there's only one of those. So I multiply by 1. The next one, the mean is 3. But 3 minus 3 squared. And how many 3's are there? There's 6 of them. So you can either write it out 6 times, which is kind of crazy, or you can just multiply by 6, and that's the same as adding it 6 times. Okay? And then I'm going to continue down here. The next data point is 4, so I'm going to do 4 minus 3 squared, and I've only got one of those. And the last one is 5 minus 3 squared, and I only have one of those. Okay? So all of those, that's in the numerator, and then in the denominator, I have n, okay? So that's 1 plus 1 plus 6 plus 1 plus 1. Okay, so when I do this in my calculator, so you can either do it by hand or you can do it in your calculator. If you're going to do this in your calculator, it might take you a little while. Okay, so what I would do is I would write parentheses, and I do 1 minus 3, close parentheses, and I hit the square button. And then what would I do? I'd do plus, not minus, plus, and then parentheses 2 minus 3, close parentheses, square it, plus, and now there's 6 of these, so 6 times parentheses 3 minus 3, close parentheses, square it, plus, and then parentheses 4 minus 3, close parentheses, square it, and then plus, parentheses 5 minus 3, close parentheses, square it, hit enter, and I get 10. Okay, so the numerator is 10. The denominator adds up to 10. So this equals 1. So sigma squared, so the first population sigma squared, the population variance is 1. Now, how do I get the standard deviation? To get back into my original units, the same unit as the problem started in, well, I take the square root. The square root of sigma squared, that's equal to the square root of 1, which is still just 1. Okay? So this has a population standard deviation equal to 1, and it has a mean equal to 3. Okay? The next one, if I do this again, and it might be good for you to try this one out. So if you think about it, so sigma squared, we do the sum of what? It's the weight, right, multiplied by the x minus the mean squared. The weight for typically is 1 for each of them, but that's why we didn't write it in this formula up here, because typically that's just 1. But since this one's a little bit of an oddball, I'm kind of throwing something else at you. So this is equal to that right there. So how do I do it? Well, the first one has an x value of 1, right? So the first x value is 1. So it's 1 minus, what's the average? The average we found to be 3 squared. So if you're going to find the population variance or standard deviation, what do you have to know? You have to find the average first. Okay, so that's something you might want to keep note of. You got to find the average first before you can get the variance or standard deviation. Okay, so we do that. And how many of them are there? There's 3.5 of them. So I'm going to take that and multiply by 3.5. The next one is going to be 2 minus 3 squared. There's only one of those. And then there's 3 minus 3 squared, and there's only one of those. And then there's 4 minus 3 squared. There's only one of those. And then there's 5 minus 3 squared. But the 5 minus 3 squareds have 3.5. So I'm going to put 3.5 on the outside here. Okay? So, and then I take all that and I divide by what? I divide by 3.5 plus 1 plus 1 plus 1 plus 3.5. And when I do this math, I'm going to get 30 divided by 10, which equals 3. So that tells me sigma squared of the second population is 3. So if I take sigma of the second population, that's a standard deviation. It's the square root of 3, which is roughly 1.73. Okay? So this population has a mean of 3 and a population standard deviation of 1.73. Okay? So what does the standard deviation tell us, all right? If the standard deviation was 0, that would mean like all of the data was centered, like all 10 things were centered on the one value, okay? So that means like every x is 3, and then every average is, the 3 is what it averages to, because if you got a bunch of 3s, like 10 times, right? It's all going to average to 3. And so when you do those x minus mu's squared, you get 3 minus 3, which is 0. That's why when you add all those up, you get 0. That would be the only way. If you saw a population where every number was the same, that would be the only way you could get a standard deviation of 0. And that's the smallest variation from the mean you can be. Think of standard deviation as a distance, right? It's a measurement of how far away we are from the mean, okay? That's in essence what we're doing. An average distance of how far away we are from the mean, okay? So what do I do now? All right, well, I noticed that the second population has a standard deviation that is bigger than the first population. So the standard deviation here is greater than the standard deviation of the first population. What does that mean? What does that really mean to us? That means that the data from population 2 is more spread out from the mean than the data from population 1. From population 1, it looks like most of the data is centered around the mean, which gives it the smaller standard deviation compared with the second population. Okay? So hopefully that helps you understand a little bit more what's going on with those standard deviations and why it's actually important that we have mean and standard deviation. The mean tells us where it's centered. The standard deviation tells us how spread out we are from where it's centered. Okay? So 2 very important measurements when we're talking about distributions. And by the way, guys, we're going to use those measurements for the rest of the class. So we need to know how to do population variance and population standard deviation, absolutely.